I want to describe the most successful scientific theory in the history of human thought. Not the most famous, not the most dramatic, the most successful in the precise sense that its predictions have been confirmed to a greater degree of accuracy against a wider range of physical phenomena than any other theoretical framework ever constructed. The theory is the standard model of particle physics. It describes in a single mathematical framework all known elementary particles and three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force. It was assembled over roughly 50 years, from the late 1940s to the early 1970s, by several dozen physicists working on both the theoretical and experimental sides. It has been tested against thousands of experimental measurements at energies ranging from the subatomic to the hundreds of billions of electron volts available at the Large Hadron Collider. Every measurement has been consistent with its predictions. I want to take you through the full story of the Standard Model, because the story is more interesting than most popular accounts suggest. It is not a story of a single flash of insight that revealed the structure of matter. It is a story of multiple independent developments, some theoretical and some experimental, some accidental and some deliberate, that converged in the early 1970s into a framework so comprehensive and so precise that it still stands today, 50 years later, as the foundation of our understanding of the physical world. But I also want to be honest about what the Standard Model is not. It is not the final theory. It is not a theory of everything. It does not include gravity. It does not explain dark matter. It does not explain why there is more matter than antimatter in the universe. It has approximately 19 free parameters, numbers that must be measured and put in by hand rather than derived from first principles. These are genuine incompleteness. The Standard Model is the most successful theory in science, and it is incomplete. Both of these things are true simultaneously, and understanding both is essential for understanding where physics is today and where it is going. Let me start at the beginning, not the beginning of the Standard Model itself, but the beginning of the enterprise of understanding what matter is made of, because the Standard Model is the current endpoint of a journey that started 2,500 years ago with the Greek philosophers who first asked whether matter is continuous or discrete. Democritus and Leucippus proposed in the 5th century BCE that matter is composed of indivisible particles, atoms, moving through empty space. Their argument was philosophical rather than empirical. If you divide matter indefinitely, you either reach something indivisible, the atom, or you reach nothing. If matter is infinitely divisible, there is nothing to divide, and matter cannot exist. Therefore, matter must be composed of atoms. This argument was not taken seriously by most ancient philosophers, particularly not by Aristotle, whose influence dominated Western thought for nearly 2 millennia. Aristotle's continuous matter view prevailed. The atomic theory was largely forgotten until the 17th century, when mechanical philosophers like Gassendi and Boyle revived it, and the 18th century, when John Dalton gave it its first quantitative form. Dalton's atomic theory, developed in the first decade of the 19th century, proposed that each chemical element is made of atoms of a specific mass, and that chemical reactions are rearrangements of these atoms. The theory explained the law of definite proportions, the observation that chemical compounds always contain their constituent elements in fixed mass ratios. Water is always 8 grams of oxygen per gram of hydrogen. Carbon dioxide is always 2. 67 grams of oxygen per gram of carbon. The fixed ratios are a consequence of the discrete atomic nature of matter. But Dalton's atoms were phenomenological. They were posited to explain the chemical regularities, but their internal structure was unknown. The question of what the atoms are made of, whether they are truly indivisible or whether they have internal structure, would be answered only in the late 19th and early 20th centuries. The discovery of the electron by J.J. Thomson in 1897, through measurements of cathode rays in evacuated tubes, established that atoms contain negative charges that can be separated from the atom. The atom is not indivisible. Ernest Rutherford's gold foil experiment in 1909, in which he and Geiger and Marsden measured the deflection of alpha particles by a thin gold foil, revealed that most of the atom's mass is concentrated in a tiny, dense nucleus, approximately 10,000 times smaller than the atom itself. The nuclear model of the atom replaced Thomson's plum pudding model. The nuclear model raised the question of what holds the nucleus together. The nucleus contains protons, which are positively charged, packed into a volume a few femtometers across. The electrostatic repulsion between these charges is enormous. Something must overcome it. That something is the strong nuclear force, a new force that operates only at very short distances but is enormously stronger than electromagnetism. The proton itself is not a fundamental particle. This was discovered at SLAC, the Stanford Linear Accelerator Center, in the late 1960s, in deep inelastic scattering experiments that fired high-energy electrons at protons and measured the scattered electrons at large angles. The scattering pattern revealed that the proton contains hard, point-like constituents that Feynman called partons and that were later identified as quarks. The particles proposed by Murray Gell-Mann and George Zweig in 1964. By the early 1970s, the picture had crystallized. Matter at the deepest accessible level consists of two types of fundamental particles: quarks, which feel the strong force, and leptons, which do not. The electron is a lepton. The up and down quarks are the constituents of protons and neutrons. These particles interact through forces, and the forces are mediated by gauge bosons. The photon mediates the electromagnetic force. The W and Z bosons mediate the weak force. The gluons mediate the strong force. This is the standard model. Let me now describe the mathematical structure that underlies it, because the mathematical structure is what makes the theory so precise and so powerful. If this is already shifting how you think about the nature of matter and the structure of reality, the principles I have developed through decades of thinking about these ideas are collected in my book, Ready to Change How You See the World? Get your copy of 12 Principles for Understanding the Fabric of Reality at realityprinciples.com. The standard model is a quantum field theory. A quantum field theory is a theoretical framework that combines the principles of quantum mechanics with the principles of special relativity. It is the natural language for describing particles and their interactions at high energies, where both quantum effects and relativistic effects are important. In a quantum field theory, the fundamental objects are not particles but fields. A field is a mathematical object that assigns a value to every point in space-time. The electron field, the photon field, the Higgs field, all are fields that permeate all of space. Particles are not separate entities floating in empty space. They are quantized excitations of these fields, localized disturbances that propagate through the field medium. The specific quantum field theories that make up the standard model are gauge theories. A gauge theory is a field theory with a specific type of mathematical symmetry called a gauge symmetry. A gauge symmetry is a local symmetry. The transformation can vary from point to point in space-time. The requirement that the theory be invariant under local gauge transformations forces the existence of force-carrying particles. Let me make this precise. Consider the electron field, which is a spinor field. The simplest gauge symmetry of the electron field is a local U1 phase symmetry. You can multiply the electron field at each point in space-time by a different complex phase, and the physics should remain unchanged. For this local invariance to hold, you must introduce a gauge field that compensates for the varying phase. That gauge field is the electromagnetic field. The photon is the quantum of the electromagnetic gauge field. This is the deep connection between symmetry and forces. The electromagnetic force exists because of the local U1 gauge symmetry of the electron field. The mathematical requirement that the theory be locally invariant forces the photon into existence. It is not put in by hand, it is required by the symmetry. The same principle applies to the weak and strong forces. The weak force corresponds to a local SU2 gauge symmetry, and it requires 3 gauge bosons, the W plus, the W minus, and the Z boson. The strong force corresponds to a local SU3 gauge symmetry, and it requires 8 gluons. The full gauge symmetry group of the standard model is SU3 times SU2 times U1, and the requirement that the theory be invariant under this group forces all the force-carrying particles into existence. The matter particles, the quarks and leptons, are the matter on which the forces act. The quarks come in 6 types called flavors: up, down, strange, charm, bottom, and top. The leptons also come in 6 types: the electron, the muon, the tau, and 3 neutrinos, 1 for each of the charged leptons. These 12 matter particles, along with their antiparticles, are organized into 3 generations of increasing mass. The first generation contains the up quark, the down quark, the electron, and the electron neutrino. These are the lightest and most stable particles. The proton and neutron are made of first-generation quarks. The electron is a first-generation lepton. Everything in ordinary matter consists of first-generation particles. The second generation contains the charm quark, the strange quark, the muon, and the muon neutrino. These are heavier than first-generation particles and decay into first-generation particles typically on timescales of microseconds or less. The discovery of the muon and cosmic ray experiments in 1936 prompted the physicist I. Rabi, to ask, who ordered that? The muon was not expected, not needed for any known physics, and appeared to be a heavier copy of the electron for no obvious reason. The third generation contains the top quark, the bottom quark, the tau, and the tau neutrino. The top quark, discovered at Fermilab in 1995, is the heaviest known fundamental particle with a mass approximately 173 times that of the proton. It decays so quickly in approximately 10 to the minus 25 seconds that it does not have time to bind with other quarks into hadrons before it decays. It is the only quark we can study in isolation. The 3-generation structure of the Standard Model is one of its most mysterious features. There is no theoretical explanation within the Standard Model for why there are exactly 3 generations, why the masses increase from generation to generation, or why the mass ratios between generations are what they are. The masses of the fermions are free parameters of the theory, put in by hand to match observation. The structure we have been exploring, the way symmetry dictates forces, the way particles organize into patterns, reflects something profound about how reality is built. These kinds of deep patterns are what I explore in my book. 12 principles grounded in the deepest science made actionable. Get 12 principles for understanding the fabric of reality at realityprinciples.com. The Standard Model is a quantum field theory. A quantum field theory is a theoretical framework that combines the principles of quantum mechanics with the principles of special relativity. It is the natural language for describing particles and their interactions at high energies, where both quantum effects and relativistic effects are important. In a quantum field theory, the fundamental objects are not particles but fields. A field is a mathematical object that assigns a value to every point in space-time. The electron field, the photon field, the Higgs field, all are fields that permeate all of space. Particles are not separate entities floating in empty space. They are quantized excitations of these fields, localized disturbances that propagate through the field medium. Let me develop this more carefully, because the concept of a quantum field is one of the most counterintuitive in all of physics and one of the most important for understanding the Standard Model. In classical field theory, a field is a function that assigns a number or a vector to every point in space. The temperature distribution in a room is a classical scalar field. The electric field around a charged particle is a classical vector field. These fields are not made of discrete objects. They vary continuously. In quantum field theory, the field is promoted to an operator. It becomes a mathematical object that, when acting on quantum states, creates or destroys particles. The electron field, when its Fourier components are interpreted quantum mechanically, contains creation operators that produce electrons and annihilation operators that destroy them. A free electron is a single quantum of the electron field, a specific excitation of the field at a specific momentum. This picture resolves a puzzle that bedeviled early quantum mechanics. How can particles be created and destroyed? In non-relativistic quantum mechanics, the number of particles is conserved. But in experiments at high energies, particles are created and destroyed routinely. An electron and a positron annihilate to produce photons. Proton-antiproton collisions produce hundreds of new particles. Quantum field theory handles this naturally because particles are just excitations of fields, and excitations can be created and destroyed. The specific quantum field theories that make up the Standard Model are gauge theories. A gauge theory is a field theory with a specific type of mathematical symmetry called a gauge symmetry. A gauge symmetry is a local symmetry. The transformation can vary from point to point in space-time. The requirement that the theory be invariant under local gauge transformations forces the existence of force-carrying particles. Let me make this precise. Consider the electron field, which is a spin-or field described by a four-component complex-valued function of space-time. The simplest gauge symmetry of the electron field is a local U1 phase symmetry. You can multiply the electron field at each point in space-time by a different complex phase e to the I times theta of x, where theta is an arbitrary function of space-time position, and the physics should remain unchanged. If the theory contained only the electron field with a kinetic term, this local invariance would be violated. The derivative of the field would pick up an extra term proportional to the derivative of theta. To restore the invariance, you must add a gauge field, a four-vector field A sub mu, and modify the derivative to include a coupling to A. The modified derivative, called the covariant derivative, transforms correctly under the gauge transformation when A transforms simultaneously as A goes to A plus the gradient of theta. The gauge field, A sub mu, is the electromagnetic four potential. Its quantum excitations are the photons. This is the deep connection between symmetry and forces. The electromagnetic force exists because of the local U1 gauge symmetry of the electron field. The mathematical requirement that the theory be locally invariant forces the photon into existence. It is not put in by hand. It is required by the symmetry. The same principle applies to the weak and strong forces, but with larger gauge groups. The weak force corresponds to a local SU2 gauge symmetry. SU2 is the group of 2 by 2 unitary matrices with determinant 1. A local SU2 gauge symmetry requires 3 gauge bosons corresponding to the 3 generators of SU2. These 3 bosons are the W plus, the W minus, and the neutral W0. The strong force corresponds to a local SU2 3-gauge symmetry, the group of 3 by 3 unitary matrices with determinant 1. SU3 has 8 generators requiring 8 gauge bosons. These 8 bosons are the gluons. Each gluon carries a combination of color and anticolor charge from the SU3 symmetry. The full gauge symmetry group of the Standard Model is SU3 times SU2 times U1. This means the standard model has three separate gauge symmetries, one for each force, and the force-carrying particles of each force are required by the invariance under the corresponding gauge transformation. The matter particles, the quarks and leptons, are organized into representations of this gauge group. A quark transforming in the fundamental representation of SU3 has three color states: red, green, and blue. It also transforms under SU2 and U1 in specific ways that determine how it interacts with the W bosons and the photon. A lepton does not transform under SU3, meaning it is a color singlet and does not feel the strong force. The Lagrangian of the standard model, the mathematical object from which all of the theory's predictions are derived, is a sum of kinetic terms for all the fields, gauge interaction terms, that couple the matter fields to the gauge fields and the Higgs sector. The gauge interaction terms are completely determined by the gauge group and the representations of the matter fields. Once you specify SU3 times, SU2 times, U1, and the representations of the quarks and leptons, the form of all interactions is fixed. This is the extraordinary economy of the standard model. From the specification of a gauge group and matter content, everything else follows from the requirement of gauge invariance and renormalizability. The specific structure of how quarks and leptons interact with photons, W bosons, Z bosons, and gluons is all contained in the mathematical requirement of local gauge invariance. Let me now describe quantum chromodynamics, the theory of the strong force, in more detail, because it has several properties that are qualitatively different from electromagnetism and are essential for understanding why quarks are confined inside hadrons. Quantum chromodynamics, QCD, is the SU3 gauge theory of the strong force. The fundamental matter particles that feel the strong force are quarks. Each quark carries one of three color charges: red, green, or blue. The 8 gluons carry combinations of color and anticolor charge, and they mediate the interactions between quarks. The key feature of QCD that distinguishes it from electromagnetism is that the gluons carry color charge themselves. In electromagnetism, the photon is electrically neutral and does not interact with itself at tree level. In QCD, the gluons carry color charge and interact with each other. This self-interaction of the force carriers makes QCD a non-abelian gauge theory and gives it qualitatively different behavior from electromagnetism. The most important consequence of the gluon self-interaction is asymptotic freedom. At short distances, or equivalently at high energies, the strong coupling constant becomes small. Quarks interact weakly with each other at very high energies. This is why deep inelastic scattering experiments see quarks behaving like nearly free particles inside the proton. At the high momentum transfers involved, the coupling is small and the quarks are weakly bound. At long distances, or equivalently at low energies, the strong coupling becomes large, the effective coupling grows as you try to pull quarks apart. If you try to separate two quarks, the energy in the color field between them grows. When the energy becomes large enough, it is energetically favorable to create a new quark-antiquark pair from the vacuum. The new quarks immediately bind to the original quarks, creating two mesons instead of two free quarks. You can never isolate a single free quark. This is quark confinement. The mechanism of confinement is one of the most important unsolved problems in theoretical physics. We know confinement happens because we have never observed a free quark. Lattice QCD calculations, which simulate QCD on a discrete space-time grid using computer algorithms, have demonstrated confinement numerically and have calculated the hadron mass spectrum with precision. But an analytical proof of confinement from first principles in QCD has not been achieved. The Clay Mathematics Institute has offered a $1 million prize for a mathematical proof of the existence of a mass gap in pure Yang-Mills theory, which is closely related to confinement. The proton and neutron, the constituents of ordinary atomic nuclei, are hadrons, bound states of quarks held together by the strong force. The proton contains 2 up quarks and 1 down quark, while the neutron contains 1 up quark and 2 down quarks. The quarks in these hadrons are constantly interacting through gluon exchange with additional quark-antiquark pairs, C-quarks, appearing and disappearing from the vacuum. The mass of the proton is approximately 938 MeV, but the current masses of the up and down quarks are only approximately 2.3 and 4.8 MeV respectively. More than 99% of the proton's mass comes from the kinetic energy of the quarks and the energy of the gluon field, not from the quark masses. This is the origin of most of the visible mass in the universe. The Higgs mechanism gives mass to the quarks and charged leptons through Yukawa couplings, but these masses are dwarfed by the QCD-generated masses of the hadrons. The Higgs gives the electron its mass of 0.511 MeV. The Higgs gives the up quark its mass of 2.3 MeV. But the proton, made of quarks with Higgs-generated masses of a few MeV, has a mass of 938 MeV, almost entirely from the strong force dynamics. The 3-generation structure of the Standard Model is one of its most mysterious features. The quarks and leptons are organized into 3 copies, with the 2nd and 3rd generations being heavier and unstable copies of the first. There is no theoretical explanation within the Standard Model for why there are exactly 3 generations, why the masses increase from generation to generation, or why the mass ratios between generations are what they are. The masses of the fermions are free parameters of the theory, put in by hand to match observation. The specific numbers are striking in their arbitrariness. The top quark is approximately 40,000 times heavier than the up quark. The tau lepton is approximately 3,500 times heavier than the electron. There is no pattern in the mass ratios that suggests an underlying structure. They appear to be arbitrary numbers, which is deeply unsatisfying for a theory that claims to be fundamental. Now let me take you to the most dramatic episode in the history of the Standard Model, the prediction and discovery of the Higgs boson. The electroweak theory, developed by Glashow, Salam, and Weinberg in the 1960s, unified the electromagnetic and weak forces into a single gauge theory. The unification required that the W and Z bosons be massless, like the photon, in the symmetric phase of the theory. But the W and Z bosons are observed to be massive, with masses of approximately 80 and 91 GeV. The massless prediction of the symmetric electroweak theory is wrong. The resolution is the Higgs mechanism, proposed in 1964 by Peter Higgs, Francois Englert, and Robert Brout independently. The Higgs mechanism introduces a scalar field, the Higgs field, that acquires a non-zero value in the ground state of the universe. This non-zero vacuum expectation value of the Higgs field breaks the electroweak symmetry spontaneously. The W and Z bosons acquire mass by interacting with the Higgs field. The photon remains massless because it couples to a combination of gauge fields that is preserved by the spontaneous symmetry breaking. The Higgs boson is the quantum of the Higgs field, the particle produced when the Higgs field is disturbed from its ground state value. The prediction of the W and Z bosons from the electroweak theory was confirmed in 1983 at CERN, when Carlo Rubbia, Simon Vandermeer, and their collaborators detected W bosons and Z bosons in proton-antiproton collisions at the super-proton synchrotron. The measured masses, approximately 80 and 91 GeV, match the electroweak theory's predictions given the other measured parameters of the theory. Rubia and Vandermeer received the Nobel Prize in Physics in 1984, just 1 year after the discovery, one of the fastest Nobel Awards in the prize's history. The Higgs boson remained unobserved for nearly 5 decades after its theoretical introduction. Finding it required a particle accelerator capable of producing collisions at energies high enough to excite the Higgs field significantly. The Large Hadron Collider was designed in part specifically for this purpose. The Higgs boson was finally discovered on the 4th of July 2012 in simultaneous announcements by the ATLAS and CMS collaborations at CERN. Both experiments observed a new particle at a mass of approximately 125.09 GeV with properties consistent with the Higgs boson predicted by the Standard Model. The statistical significance of the discovery was above 5 sigma in both experiments. Peter Higgs and Francois Englert received the Nobel Prize in Physics in 2013. The discovery of the Higgs boson was the culmination of 50 years of development of the Standard Model. It was the confirmation of the last major prediction of the theory. The Standard Model was complete. Now let me describe the precision with which the Standard Model has been tested, because the numbers are extraordinary and deserve to be stated precisely. The most precise prediction of the Standard Model, and perhaps the most precisely confirmed prediction in all of science, is the anomalous magnetic moment of the electron. The electron, according to Dirac's equation, should have a magnetic moment exactly equal to 1 Bohr magneton, corresponding to a G factor of exactly 2. But quantum corrections modify this prediction. Virtual photons, virtual electron-positron pairs, and virtual other particles running in loops all modify the electron's interaction with magnetic fields. The theoretical prediction for the anomalous magnetic moment, a subscript E, is now known to 11th order in perturbation theory, involving more than 10,000 Feynman diagrams. The theoretical prediction is a subscript E equals 0.0011596521817 plus or minus 0.00000000077. The experimental measurement performed by Gabriels and collaborators using a single electron stored in a Penning trap is a subscript E equals 0.001159652187073 plus or minus 0.00000000028. The agreement is at the level of 1 part in 10 to the 12th. This is the most precise agreement between theory and experiment in the history of science. The precision of the Standard Model predictions for electroweak observables is also extraordinary. The Z boson mass has been measured at LEP to be 91,187.6 plus or minus 2.1 MeV. The Standard Model predicts it from other parameters to an accuracy consistent with this measurement. The W boson mass is predicted to approximately 10 MeV precision. The weak mixing angle, which determines the ratio of the Z and W boson masses, is measured at the parts per million level and agrees with the Standard Model. The strong coupling constant, which determines the strength of the strong force, is measured from dozens of independent processes, from deep inelastic scattering to jet production to lattice QCD calculations of hadron masses, and all measurements are consistent with a single value, approximately 0.118 at the Z boson mass scale. These are not approximate agreements. They are precise agreements, checked at the level of quantum corrections and higher order effects involving calculations of extraordinary difficulty. The Standard Model has been tested not just at leading order, but at next to leading order, next to leading order, and beyond. The theory continues to pass every test. What I find most profound about the Standard Model is what it reveals about the relationship between mathematics and reality. The universe has a structure that we can describe with extraordinary precision, and that structure is not arbitrary but follows from deep principles. I have distilled 12 of these principles into my book, Ready to Change How You See the World? 12 Principles for Understanding the Fabric of Reality. Get your copy at realityprinciples.com. Let me now describe the specific ways in which the Standard Model is incomplete, because this is as important as understanding its successes. The incompleteness is not a flaw of the theory, but a window into what lies beyond it. The most obvious incompleteness is the absence of gravity. The Standard Model describes 3 of the 4 fundamental forces, but not gravity. General relativity, Einstein's theory of gravity, is a separate theoretical framework that operates on completely different principles. General relativity is a classical field theory. The Standard Model is a quantum field theory. The two frameworks are mathematically inconsistent with each other at the Planck scale, where quantum gravity effects become important. The quantization of gravity is one of the most important unsolved problems in theoretical physics. Attempts to apply the methods of quantum field theory directly to general relativity produce a non-renormalizable theory. The quantum corrections are infinite in a way that cannot be absorbed by redefining the parameters of the theory. String theory and loop quantum gravity are the two most developed approaches to quantum gravity, but neither has produced a complete, confirmed theory. At the energy scales accessible to current experiments, gravitational effects on particle physics are completely negligible. The gravitational force between two electrons is approximately 10 to the minus 43 times the electromagnetic force between them. Gravity can be safely ignored in all particle physics calculations. But the fundamental incompatibility between general relativity and the Standard Model tells us that neither is the final theory. The second incompleteness is dark matter. Approximately 27% of the energy content of the universe is in the form of dark matter, which interacts gravitationally but does not emit, absorb, or scatter light. Dark matter is not composed of any known Standard Model particle. The neutrinos, the lightest Standard Model particles, were proposed as dark matter candidates but have been ruled out by observations showing that dark matter is cold, not hot, and by measurements of the neutrino masses. The best dark matter candidates involve particles beyond the Standard Model, weakly interacting massive particles, axions, sterile neutrinos, or other hypothetical species. The third incompleteness is dark energy. Approximately 68% of the energy content of the universe is in the form of dark energy, which drives the accelerating expansion of the universe. The simplest model of dark energy is a cosmological constant, equivalent to a constant energy density of the vacuum. The Standard Model predicts that the vacuum has energy from quantum field fluctuations, but the predicted vacuum energy density is approximately 120 orders of magnitude larger than the observed dark energy density. This is the cosmological constant problem, one of the most severe discrepancies between theory and observation in all of physics. The fourth incompleteness is the matter-antimatter asymmetry. The Standard Model predicts that the Big Bang should have produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate, producing photons. If the universe began with equal amounts, all matter should have annihilated with all antimatter, leaving a universe filled with photons and no matter. But we exist, made of matter, in a universe that contains matter. There must have been a slight asymmetry in the initial conditions, approximately 1 extra particle of matter per billion particles of antimatter that survived the annihilation. The Standard Model contains a small amount of CP violation, the asymmetry between the behavior of particles and their antiparticles from the complex phases in the quark mixing matrix. But the amount of CP violation in the Standard Model is far too small to explain the observed matter-antimatter asymmetry of the universe. New sources of CP violation beyond the Standard Model are required. The fifth incompleteness is the hierarchy problem, which I described in the CERN video. The Higgs mass of 125 GeV is extraordinarily sensitive to quantum corrections, which would naturally drive it to the Planck scale without fine-tuning of the parameters to 1 part in 10 to the 34. The sixth incompleteness is the strong CP problem. The strong force could in principle violate CP symmetry, the combined symmetry of charge conjugation and parity. The standard model contains a parameter theta QCD that would generate CP violation in the strong sector if it is non-zero. Experimental measurements of the neutron electric dipole moment constrain theta QCD to be less than approximately 10 to the minus 10, an extraordinarily small value. There is no known reason within the standard model for theta QCD to be so small. This is the strong CP problem. The seventh incompleteness is neutrino mass. The original standard model predicted massless neutrinos, but experiments in the 1990s and 2000s demonstrated that neutrinos oscillate between different flavors, a phenomenon that requires the neutrinos to have non-zero masses. The Super Kamiokande experiment in Japan found evidence for atmospheric neutrino oscillations in 1998, and the SNO experiment in Canada confirmed solar neutrino oscillations in 2002. The Nobel Prize in Physics was awarded for these discoveries in 2015. Neutrino masses are now incorporated into the standard model, but the mechanism for generating them is different from the mechanism that gives masses to the quarks and charged leptons. The small size of the neutrino masses, less than approximately 0, 1 electron volt compared to the electron mass of 511,000 electron volts, suggests a different mass generation mechanism, potentially involving a seesaw mechanism with very heavy right-handed neutrinos beyond the standard model. Each of these incompleteness points to physics beyond the standard model. Each is a window into a deeper theory. The standard model is extraordinary in what it explains and extraordinary in what it leaves unexplained. Both are true and both are important. The standard model tells us something profound. The deepest level of reality we can access is structured, mathematical, and comprehensible. That insight that the fabric of reality follows discoverable principles is the foundation of my book, Ready to Change How You See the World? 12 Principles for Understanding the Fabric of Reality. Get your copy at realityprinciples.com. What principle from today's discussion resonated with you most? Let me know in the comments. Let me close with what I think is the most important thing to say about the standard model, which is about its relationship to science as a human enterprise. The standard model was not discovered by a single genius working alone. It was assembled by hundreds of physicists working over decades, each contributing a piece, each building on the work of the others. The electroweak theory emerged from contributions by Glashow, Salam, and Weinberg, each approaching the problem from a different angle. The renormalizability of the theory was proved by Hooft and Veltman, who received the Nobel Prize in 1999 for this work. The quark model was proposed independently by Gell-Mann and Zweig. Quantum chromodynamics, a theory of the strong force, was developed by Fritzsche, Gell-Mann, and Leutwiler, building on work by Yang and Mills on non-abelian gauge theories. The asymptotic freedom of QCD, the property that the strong force becomes weaker at short distances, was discovered by Politzer, Wilczek, and Gross, who received the Nobel Prize in 2004. This is how science works at its best, a collective enterprise, self-correcting, building incrementally, testing every claim against experiment, and occasionally achieving a synthesis that captures something deep and true about the structure of the universe. The standard model captures something deep and true. It is not the final word, it is the current word, and it is extraordinary. The universe, at its deepest accessible level, is described by the symmetries of SU, 3 times SU, 2 times U1, realized in quantum fields that permeate all of space, interacting through the exchange of gauge bosons with matter organized into 3 generations of quarks and leptons and masses generated by the Higgs mechanism. This is what we know. It is a triumph. And the open questions, dark matter and dark energy and gravity and matter-antimatter asymmetry and neutrino mass and the hierarchy problem, are the frontier. The Standard Model is not the destination. It is the map of the territory we have already explored, and the frontier is what lies beyond the edge. If this changed how you think about the Standard Model and the quantum particle physics, tell me in the comments. Tell me which aspect you find most remarkable. The extraordinary precision of the electron magnetic moment calculation, the way local gauge symmetry forces the existence of force-carrying particles, or the list of open problems that point beyond the theory. And subscribe if you want to keep going into the places where the most precise theory in science meets the open questions it cannot yet answer.